Hello and welcome back. We're going to talk about Introduction to Statistics, and this is starting to set the background for understanding statistical geometry of fiber networks. So in particular today we're going to talk about a couple of different things. Statistics in general is the study of random numbers and random events which occur that we can add a number to or place a number to. And when we talk about statistics, we usually talk about two types of variables. Variables that take on discrete values, and then variables that can take on a wide range or an infinite number of values. And when we look at this, we can start off by talking about discrete values or discrete variables as a starting point. And discrete variables take on specific values. Now, to set some terminology to begin our discussion, I'm just going to start off by talking about two simple six-sided dice. So we have two simple six-sided dice, and a six-sided dice is just a cube. And on each side of these, one side will have one dot, two dots, three dots, up to six dots. So this side might have 1, 2, 3, 4, 1, 2, 3, 4, 5, and over here we have a total of 6 dots. So there's two different die, and each one of these dice or die has a dot on its side up to 6 to label the different sides. So when we take these two dice and we're going to go and we're going to roll these dice, we have a certain number of sides that can come up, and basically we have one of the 6 sides is going to turn up. So the total number of different combinations of sides that we have are 6 sides on the first dice times 6 sides on the second dice. So we have a total of 36 different combinations of sides that could come up when we roll these two dice. So looking at this, we don't know which are going to come up, and if we do this correctly, and these are fair dice, we should come up with a random set of numbers. Now we'd like to know the probability of each of these numbers. So what are the different numbers that could come up on each side? We'll call these different numbers x, and x is going to be a discrete variable. So when we roll these dice, we're going to get a number that's going to be somewhere between 2 and 12. So it's going to be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. So one of those particular variables is going to come up. So we would like to know what is the probability of each of these numbers occurring. And if you can imagine what the practicality of this might be, if you were a gambling man, you might want to know this, right? You might want to know how likely is it to roll each of these different sides. We're going to say, so what's the probability of the value x occurring? And we're going to put this in the second row here, the lower row going across. Well, when we look at it, to roll the number 2, we have basically one way that we can roll the number 2, right? We have to roll a 1 on the first, and by necessity we must roll a 1 on the second. So there is a 1 in 36 way that we can come up with the number 1. Now for 3 it's a little bit different. We can roll a 1 on the first and a 2 on the second dice, or we can roll a 2 on the first and a 1 on the second. So we would actually see here that we have a 2 in 36 chance. Now for 4, we have more ways that we can make 4, and it turns out there's 3 out of 36. For 5, 5 out of 36. For 6, whoops, excuse me, I missed one here. This should be 4 out of 36, 5 out of 36, 6 out of 36, and 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and finally 1 out of 36. So this tells us the probability for finding each of these different numbers. So when we roll this dice and we add up the value on the tops of these two dice, we have to find one of these numbers up above here from 2 to 12, and corresponding below is the probability of finding each of these numbers. So if we were to roll these dice a very large number of times, this is the approximate ratios, or the ratios that we should get between these different fair dice as we roll them a large number of times. And we have some, or we have a name for p of x, and we call this the probability distribution function. So this is our probability distribution function, and it describes how the probability is distributed over the different values that the variable x can take on. So that's pretty straightforward, and that's one way that we handle this particular situation. Now there's a number of other ways that we could deal with this as well. One particular way, or I'm sorry, another type of variable that we can deal with this is something called a continuous variable. So a continuous variable is a variable that takes on an infinite set of numbers or values that can change in infinitely small increments. So let me give you a simple example of a continuous variable. Let's start off here by just arbitrarily picking an axis, and we could call this axis our 0-degree axis. So this is our 0-degree axis, and then falling down on top of this axis, so there's a plane of paper, we're going to drop a needle or an arrow. I'm just going to represent this needle or this arrow so we have direction to this arrow. Now the question we might want to ask is, if we do this a large number of times, what is the average value of this angle theta? What will it average out to be? So if we do this a large number of times, we keep dropping this down, we might like to know what the average value would be, or we might like to know the probability of this arrow landing at a certain angle. So how do we determine that? Well, we can determine this from the probability distribution function. Now for our particular situation, we can talk about p of theta, and this is the probability distribution function like I'd given you before. Now the angle here can take any different number we'd like. So it could be at 45 degrees, it could be at 46 degrees, it could be at 45.5 degrees, it could be at 45.6 degrees, it could be at 45.61 degrees, it could be at 45.611 degrees. But the point being that we have an infinite number of values that it could take, and in fact it could take an infinite number of values between any two single points. So there's an infinite number of values or selections that we can place. Now if we apply the situation that we talked about before and say, take that probability of a particular event occurring divided by the number of possible events that could occur, we would say that what's the probability of this angle being 45 degrees? Well, we could compute this simply, so that's one possible situation is 45 degrees. What are all the possible angles that this could fall at? How many numbers of different angles are there? Well, there's an infinite number. So when we look at this, you would see that the probability of this occurring, or the arrow actually falling at exactly 45 degrees is 0. So when we look at probability distribution functions, the likelihood of a single event occurring under a continuous variable, the likelihood of that single event, that one specific event occurring, is actually 0. And when you think about this, this is sort of strange, because this tells you that the probability of the angle being 45 degrees, this needle falling, and the angle being 45 degrees is 0. In fact, it tells you the probability of this needle falling and that angle being any one specific value is 0. So we can't tell what the probability is. So the probability of this falling at a specific angle is 0, yet when it does fall, it must fall at a specific angle. So this sort of creates a gap in our thinking here, and I'm not going to try to explain that here, but for now I'll show you a different way to handle these probability challenges. So rather than looking at a specific value, 45 degrees, we typically look at something like a range of values. So we might look at what's the probability of this falling between 45 degrees and 90 degrees. So we could look at the probability of this arrow falling within this range of degrees, and to determine that we would simply integrate from 45 degrees to 90 degrees the probability density function as a function of theta. Okay. Now, if we assume in this particular case that the likelihood of the arrow falling at any angle is equal, we can actually determine this quite simply. We could look at this and say, well, this 45 degree range here is equal to 1/8 of our 360 degrees. Therefore, the probability must be equal to 1/8. So P 45 degrees has to equal 1/8. So that's fairly simple to determine here. So the probability of that fiber falling within that range for or uniformly distribution of probability would actually be 45 degrees. Or I'm sorry, value of 1/8. Okay? So this particular situation would assume something like this. So here, let's say, is minus 180 degrees. Here's plus 180 degrees. And the probability is uniformly distributed over these different angles. So if we were to look at 45 degrees, we would see this area here. We could break this here as 90. Any one of these sections of 45 degrees going across, breaking these down into 45 degree sections here, is equal to 1/8 of the total probability. So our probability of finding that needle or that arrow pointing within any given 45 degree section would be equal to 1/8. Now, how do we deal with probabilities where we do not have a uniform distribution of probabilities like above? For example, let's say we had a probability that looked something like this. Okay? So we have what we call a bell shape to these probabilities, and we can let this tail keep going out continuously, out infinitely, becoming smaller and smaller and smaller and approaching 0. So this is some value x over here, so the value of x, and here is the probability of x on this particular axis. How do we deal with this? Well, if you're going to study statistics, one of the most common things that we talk about is something called the normal or Gaussian distribution. So the normal or Gaussian distribution describes the distribution of probabilities for a normal or Gaussian shape. Often we'll hear this called a bell curve. And why do we call it a bell curve? We simply call it a bell curve because it sort of takes on the shape of the bell curve. Now the probability distribution function for this Gaussian distribution, or this normal distribution here, follows this form. Mu is equal to the mean value of the data set. Sigma squared is equal to the variance of the data set. And sigma is equal to the standard deviation of the data set. Now I'm making an assumption right here and right now that you guys are familiar with those basic statistical terms, the mean, the variance, and the standard deviation. If you're not familiar with those, simply accessing any statistics book will explain those to you quite thoroughly. But essentially the mean tells us the central tendency, or the centroid of the data set, the center of the data set. The variance tells us how the distribution of the data is, and the standard deviation is another measurement of the variability of the distribution of that data around the mean. So when we look at this normal distribution up above here, it actually takes on the following form, and let me explain this to you. We're going to say P of x. Now this is a bar here. Okay, this is just a placeholder here. So this probability function of the variable x is defined by two parameters, mu and sigma, or the mean and the standard deviation. And it is equal to, let me clean some of this up here. And it is equal to 1 over the square root of 2 pi sigma e to the minus 1/2 times x minus mu over sigma squared. And this is a minus 1/2 here. So that's the probability distribution function for a normal function. Now let me show you just graphically here approximately what this means as we change mu and we change the standard deviation. So this is x, and I'm going to plot here, this is P of x. I'm going to plot here two curves, a blue curve, and that blue curve is characterized by mu and sigma. Now I'm going to plot a second curve here, and this second curve is a red curve, and it's going to be characterized by mu and sigma. Now as it turns out, the normal distribution, the Gaussian distribution, is centered around its mean value of mu. So even though blue isn't drawn that well, but red's drawn better, but if we assume that they're symmetrical with the same center point here, by inspection here we can say mu blue is equal to mu red. Now the second parameter in this tells us how the data is distributed. So when we look at the distribution, we're looking at how wide or how open, how flat is this? What's the likelihood of these tails occurring? So larger standard deviations means that this is a shorter, wider curve, and there's more spread or likelihood of spread within the data. Now more narrow distributions, like the blue here, will result in a lower standard deviation and a smaller spread. So we can write another equation here, and we can say for this particular situation the standard deviation of the blue is smaller than the standard deviation of the red. Okay. Now, let me just draw a third setting on here. I'm going to pick a different color. I'll pick green. And for green, I'm going to draw another function. It's over here. And it has a different value of mu. Okay? And when we look at this, we could say that the mu for the green is less than the mu for the blue because it's centered at a different point. So very often you'll see grades described in terms of normal distributions or the bell curve, and this is why students are often interested in the values of standard deviation and mean, because it tells them how wide this data set is distributed. So if you have a very high grade and the average was very low and the standard deviation was very low, then you are a very exceptional student. If you have a very high grade and the standard deviation was high and the mean was high, you might not be such an exceptional student, although you may have scored very well. Maybe everybody in the class is an exceptional student. Okay? So that's the normal distribution. Now I rightfully can't prevent myself from not talking about this next topic here. And this next topic is called the central limit theorem. And I just want to mention this to you very briefly, because any discussion of statistics without the mention of this particular theorem would be inadequate or incomplete. So the central limit theorem is a very critical theorem that really makes statistics and analysis of our data sets work. And the central limit theorem says, okay, there's some population, okay, so there's something out here, there's some population of values that we want to measure. And the distribution, so here's, let's say, just the variable x, and this is the probability of x is plotted in this axis here. We don't know what that distribution looks like. It could look like what I drew there. It could look very different. It could look something much like this. It could look like anything, basically anything. We don't know what the probability distribution is over here, right? So we don't know what the probability distribution is. But is what we can do is we can go here and we can take samples. So I'm going to take a sample. More importantly, I'm going to take a random sample. So I'm going to take a random sample out of this population, and I'm going to collect those things together, and I'm going to make a measurement, mu, of my sample. So I'm going to measure my sample, the average value of my sample. So that's my first sample. Now I'm going to take another random sample. So I'm going to take another random sample. So this is my second sample. And again, I'm going to measure mu s. And I'm going to keep doing this. I'm going to do it over and over and over again. And I'm going to come up with a collection of mean values for my sample. So I'm going to have mu s, and I'm going to have a whole bunch of these different values. Now is what I'm going to do over here. I'm going to plot mu s and then the probability of finding mu s. So the probability of finding a particular value, mean value for my sample. And if I did this, I would find out something very interesting, very useful. I would find out that the probability distribution, here is normal. So the probability distribution of the means of a random sample, indeterminate of the distribution in the original sample, always turns out to be normal. So it doesn't matter what the probability distribution looked like in this top sample up here. Doesn't matter. Doesn't matter what these look like up here. When we get to this down here and we plot the distribution of the mean values from the samples that we took, we're going to get a log normal distribution. And why is this so critical? This is so critical because this is very often what we are actually doing in our experiments. We're taking a random sample and then we're plotting the mean values and we end up with a normal distribution, and this allows us to do our statistics quite conveniently. So while this is very important for statistics and data analysis, we're not going to use it, at least not for our work in paper physics at this point in time. We're going to use a different type of distribution. And this distribution is called the Poisson Distribution. And I'm going to give you the definition of the Poisson Distribution. So a random variable x taking values in the non-negative integers is said to have a Poisson distribution with mean lambda, and lambda is greater than 0 if the probability function of x is p, the variable x bar, so defined by lambda, is equal to e to the minus lambda, lambda raised to the x over x factorial if x equals 0, 1, 2, 3, etc. Now there's another situation. I'll draw it down here. The probability is equal to 0 otherwise. So this distribution says that the probability can be given by this value here. So the probability can be given by this value here, calculated according to this formula here, when the value of x is an integer and non-negative. If the value is anything other than a non-negative integer, the value or the probability of that occurring is 0. So this is only situations when this might occur. So why is this useful? So this becomes useful for these sort of discrete variables that take on discrete, not continuous values, but discrete variables, and that can take on a wide range. So not like our dice here where we only had a limited number of possibilities that we could roll, but we could take on just about any set of possibilities, but they have discrete values to it. So let me give you some examples of what we might use the Poisson distribution for. One thing we might use it for is number of students in a class. So when we look at the number of students that might be in a class, chances are we're going to have maybe 0, or 1, or 2, or 3, or however many students in that class, right? We can have a very large number of students in that class. But one thing we are probably quite certain of, we are not going to have 1.5 students in our class, right? So we're not going to have a half a student in a class. we're not going to have 1.75 students in a class. We're not going to have 1.9 or 1.95 students in a class. All of these things are impossible, and their probability is 0, because either the student is in the class or he's not in the class in that particular day. So that is a non-negative integer value. That could be very useful for describing different events, discrete events like that where things happen inside or out. That's one particular example. Another example might be counting marbles, or when we're actually going to count things. That's very often we'll see the Poisson distribution when we want to count different things. So let's say we want to count the number of marbles inside a bag. So we randomly put a number of marbles into the bag, and then we count the number of marbles inside that bag. So when we're counting things and we come up with these discrete values of 0, 1, 2, 3, 4, 5, that's very often where the Poisson distribution is useful. And we're going to use the Poisson distribution quite a bit in our work here. Now I'm going to tell you guys one thing you really need to memorize, because we're going to use it quite a bit here, is spend some time and memorize this function right here. Okay? Memorize this part of the function right here. After this lecture, I'd say sit down, write it down a few times, make sure you memorize it, make sure you know what it means, because we're going to refer to it a number of times. Let me just draw you a quick graph before we end here today of what a Poisson distribution might look like. So we know that it's going to have non-negative integers for our values. We would see maybe a discrete probability there at 0, then another probability at 1, that might build up to 2, 3, 4, it might stop dropping down again, 5, 6. And as the value of lambda would go up, you would see this peak shift to different locations and probability decreasing out of 0, and we would see that kind of movement as the value of lambda went up. Now I put this dotted line in here, not a solid line in here, just to show you the trend, because we have to remember outside of 0, 1, 2, 3, 4, 5, the area in here, so this area in here, there's no probability between the numbers. There's only probability associated with the discrete values. Okay? Well, thanks for your time, and we're going to pick this up again very shortly. Thanks.